Hello and welcome to this next lecture on fundamentals of acoustics. Today let us see why we take the real value. The real value. In the string, in the rod, in all these cases I say in the end we take the real value and just going to discuss why. Okay. So, we take a solution, let us say x of t now, which is a real quantity but expressed in terms of this complex variables. Okay. Now x is a real quantity, okay, and suppose I say that x at 0 is a real number p r, okay, and then a tilde is a complex number, b tilde is another complex number, okay. So that gives me a tilde plus b tilde equal to p r, and this is two conditions, okay, one real condition, one imaginary condition. Imaginary value is 0. So this gives me two conditions, okay. Now a tilde is a complex number, so there are two unknown constants, b tilde is another complex number, there are two unknown constants. So totally we have 4 unknowns, okay. Now suppose I say that x dot of 0 is another real value p I, okay. Then what do I have? I have I omega a tilde minus I omega b tilde is equal to p I. This is another two conditions, okay. So now from here what do I get? I get a tilde plus b tilde is equal to p r, and I also get a tilde is equal to b tilde minus I p I by omega. Get both of these, okay. Then if I put this in here, what do I get? I get a tilde plus a tilde plus I p I by omega is equal to p r, or a tilde is equal to 1/2 p r minus I p I by omega, okay. And then what is b tilde? B tilde is equal to a tilde plus I p I by omega, which gives me 1/2 p r minus 1/2 I p I by omega plus I p I by omega, which is equal to 1/2 p I plus 1/2 I p I by omega, okay, that is equal to a tilde conjugate, okay, that is equal to b tilde, okay. So now what do we have? What we have is x of t is A tilde e to the power of I omega t plus A tilde conjugate e to the power of minus I omega t. Okay, and that means what? 1/2 PR minus I pi by omega e to the power of I omega t plus 1/2 PR plus I pi by omega e to the power minus I omega t. Okay. So now we have taken the full solution. We have taken the full solution. What do I mean by full solution? E to the power of I omega t plus e to the power minus I omega t. And okay, we have taken the full solution with their coefficients. As a result, what has happened is B has turned out to be A tilde conjugate, and xt will be automatically, x of t is automatically real. Automatically real. Okay. How do we say that? Let us see here. If I have, I will start over. If I now have x of t is equal to A tilde e to the power of I omega t plus B tilde e to the power of minus I omega t. Okay, and A tilde is, let us say, A plus JB e to the power of I omega t, and this is, let us say, C plus JD e to the power of minus I omega t. Okay. Then what we get is, if we take just the real values, okay, so let me first expand. A plus JB cos omega t plus I sin omega t plus C plus JD cos omega t minus I sin omega t. Okay. So I get for the real A cos omega t minus B sin omega t plus C cos omega t plus D sin omega t. Okay, that is one piece of the story. Now the imaginary side, let me take this to the next page. Okay, so the imaginary story turns out to be J in front, A sin omega t plus B cos omega t minus C sin omega t plus D cos omega t. This I want 0. Why? Because x of t I want purely real, so no imaginary component. Then that implies A must be equal to C. Okay, then this cancels off, and B must be equal to minus D, then this cancels off. so that the imaginary part of x of t is 0. Okay. Then what happens with this? A is equal to c, so I get twice a, so x of t is twice a cos omega t minus twice b sin omega t. Okay. That is equal to, let us put twice a outside, a cos omega t minus b sin omega t. This I can write as twice square root of a square plus b square, the amplitude, cosine omega t plus some phase. Okay. So, this can also be written as the real part of twice a tilde e to the power of j omega t, okay, where magnitude of a tilde or a tilde, the complex number is a tilde magnitude e to the power j phi. Okay. So, that what do? I have real part twice magnitude of a tilde e to the power of j phi e to the power of j omega t, which is equal to the real part of twice magnitude e to the power of j omega t plus phi, which gives me twice magnitude of a tilde cos omega t plus of phi, and a tilde is square root of a square plus b square. Okay. So, now we have found conditions where xt is purely real. Okay. So, this is purely real. We have set it up that x of t is purely real. So, the answer has come out purely real. And why did that happen? That happened because a tilde conjugate, we forced it to be b tilde through this setting the imaginary part to 0. Okay. So, now because a tilde is what? A plus jb, and b tilde is c plus jd, but we have found that it is c minus jb or a minus jb, a minus jb from here. Okay. So, this is true, and that is how the answer has come out automatically real. Okay. But now we take part of the solution x of t, we take it as only as a part of the solution, a complex number x e to the power j omega t. Okay. We do not use the e to the power of minus j omega t. Then what happens? If I write this as magnitude of a complex number e to the power j psi, let us say, e to the power of j omega t, and this is again magnitude e to the power of j omega t plus a psi. Okay. Now, if we want a real solution like here, okay, we have not set it up like that. So, now we have to take the real part of x, so that I have this real part of this entity and that is going to be, this is a magnitude anyway, cos omega t plus psi. Okay. Now the problem and its conditions will give me x tilde to be twice magnitude A tilde and psi will be equal to phi. So that finally my answer is the same as this. Okay. Finally my answer is twice magnitude A tilde cos of omega t plus of phi. Okay. Because we are not taking the full solution, okay, like this, we are not taking the full solution, okay, we have to take the real value at the end to get our real answer. Okay. Now when you have spatial variables, okay, I have shown this only with temporal quantities. If you have spatial variables like e to the power of minus jkx or e to the power plus jkx, it becomes a little more involved, but the logic is the same. The entire solution, if it is taken, so when imposing real conditions, full solution must be taken, full solution must be taken. With all the constants. Then that means full complex solution with all constants. Then automatically the solution will turn out real. And each condition will be equal to two conditions, a real condition and an imaginary condition. Okay. If we do not do that, we have to take this, automatically real will not follow. You will have to take the real value of the quantity and it has to be imposed. Now a word about piston in the baffle, piston vibrating in a baffle. So if we have a piston vibrating in a baffle, this is the baffle as the piston. Okay. Let me mention a paper by Joe Zemanek. Okay. It is a JASA paper, Journal of Acoustical Society of America paper, 1971, volume 49 and number 1 part 2. Okay. It is titled Beam Behavior within the near field of a vibrating piston. Okay. There a special calculation is given so that you can have a closed form for the near field of the piston. If you remember, we did a Rayleigh integral which is meant for the far field. It does not give a closed form in the near field, but this paper does a special transform and acquires a closed form for us to plot and understand the near field. Now the near field, even though we are running at a harmonic single frequency which should give a single wave number, k, which means a single behavior. Okay. The thing is that when we put a piston in a baffle, the baffle has 0 velocity from infinity till the edge of the piston, and then beyond the piston again 0 velocity. It is a very harsh condition imposed, okay, till here 0 displacement and then suddenly displacement and it is a step jump. So now if you say that a single wave number should give this behavior, okay, it is not possible. It is not possible for a single wave number to give you this sudden jump, and therefore in the near field many wave numbers are generated. All of them vibrating at omega. Okay. An infinity of wave numbers k's will be generated. So continuous wave number spectrum will be generated at a single omega. Then you can have this step jump. Okay. So now when you have so many wave numbers, the near field becomes very complicated. Okay. All these wave numbers will be interacting in various ways away from the piston, so that at the piston surface they can give this boundary condition. So it will be very complicated if you plot it, and then it slowly starts to smooth, okay, in the far field. In the far field the system starts to smooth out and you will find a single wave number. Why will you find a single wave number? Because omega is 1 harmonic field. So omega by c will be one dominant frequency, spatial frequency k. But in the near field it cannot be accommodated, because one wave number can't give you this jump. So these wave numbers that are generated are evanescent. They will not be available in the far field. They decay away, and in the far field only this single k wave number will survive. Okay. So I just wanted to say that near fields of sources are very complicated. You can look at this paper and generate the results and see the near field. The paper itself plots the near field, so you can see it. It is very complicated, okay, because an infinity of wave numbers, their velocities, their pressures are interacting in the near field, which smooths away once you go slowly to the far field. Okay. I wanted to mention this. I will close the lecture here. Thank you.